In this section, 7.4, we're going to discuss the center of mass and the equations for a system of particles. In particular, we're going to again talk about the total momentum of a system. First of all, let us define what we mean by the center of mass. We define the center of mass R to be equal to the sum of each mass that we have times the position that it has. And you'll notice that this is a vector because it's a number times a vector for each particle added up over a whole set of vectors. And then we're going to divide that by the total mass, where the total mass M is given by the sum over I of all of the individual masses. This is the center of mass. Well, let's take some simple problem and see how this works out. If we were to have two masses, let's say we had two masses, and they're at points 6 kilograms here at a distance away of 5 meters. And here we have 1 meter away, we have 2 kilograms. Then first of all, let's calculate what the total mass is. Well, that's pretty simple. It's going to be 6 kilograms plus 2 kilograms, mass 1 plus mass 2, so that's going to be 8 kilograms. That gives us our total mass of the system. Well, now where's the center of mass? Well, what we have to do is we have to multiply each mass times the vector that goes towards it. So we would have this first mass, 2, times this distance 1. 2 times position 1, plus the second mass, 6 kilograms, times the position of where it is, which is 5. So we get 2 times 1 is 3, 5 times 6 is 30, so this is 33. But R is given by this divided by the total mass of the system, or 8. So now we can figure out 4 times 8 is 32, so this would be equal to position of the center of mass. The center of mass itself is going to be 4 1/8 meters. And where is that from? That's from this origin. It'll be somewhere right about here, closer to the mass that weighs 6 than the mass that weighs 2, obviously, because it weighs more. So this is how we compute the center of mass. If we had 10 objects, we just do this with 10 different terms and divide by the total mass. If they were vectors, if these masses were spread out in space, three-dimensional space, then we'd look at the vectors that went to them. And we'd have a vector R1, R2, and R3. And R1 might be a vector 6, -2, 4. R2 might be a vector 1, 1, 5. R3 might be 0, 1, 2. And if we knew what the masses were, we'd simply multiply the mass of this vector times each of its components, the mass of this one times the components, the mass of this, and then add them up. Well, let's do that. Let's say the masses are given by, at these points, 1, 2, and 1. So we'd multiply here by 1, by 2 here, by 1 here. What vectors would we end up with? Well, we can just about do this in our head. This would be 6 plus 2 times 1. Maybe I should write that out. That would be 2 times the vector, 1 times the vector R1. So that would be 6 minus 2, 4. And a 2 times the vector R2, because it had a mass of 2. And that would be 2, 2, 10. 2, 2, 10. And R3 times, again, 1, a mass of 1, would be 0, 1, 2. Now we simply add those up. So we would have 6, 7, 8. 2 minus 2 is 1. And 10, 14, 16. So this is capital R when we divide by the total mass of the system. And what is the total mass of the system? The total mass is 2, 3, 4. So this is over 4, over 4, over 4. So the R vector is going to be parentheses 2, 0.25, and 4. And this gives us our vector that goes exactly to the center of mass. You should practice that because this tells us how to do a rather complicated problem where the mass is spread out in 3 dimensions. Okay, this is how we do center of mass. I might mention that there's a way to find center of mass for an irregular object. If we have an object like this, how to find the center of mass of this is quite complex. So we have to take all these masses, add them all up, and take a vector and sum over this. Quite a complex computer program to do that. But if we just drill a small hole right there and hang this object, it turns out that the center of mass will be somewhere along this line. So if this is a string with a weight on the end, we hang the mass there, put a string with a weight on it, so I would balance that. Then we can draw a line right along there, and we know the center of mass is somewhere on that line. Then if we were to take it and turn it in the other direction so that it's hanging from this point, and we ran the line with the mass by it again, we would know the center of mass had to be on here, and we could locate the center of mass at that exact point. This is very useful for finding center of mass of very complex objects. You know, when you really don't want to add all these vectors because it's kind of hard. Well, the next thing we want to do here with our center of mass is we actually want to show a very important theorem somewhat similar to the one we showed on momentum at first. Now let's say, what have we calculated so far? What have we defined? This is section, again, this is 7.4, and the second page of that, so page B. We have defined the total momentum of the system to be equal to the momentum of the first, momentum of the second, plus momentum of the last one, which we sometimes write as the sum over I of pi. We're adding up the momenta of each particle. We have already defined the mass of the total system. It's going to be m1 plus m2 plus m3 up to mn, which is sum over I of mi. Add up all the masses. We have defined the center of mass, R. The vector that goes to the center of mass is m1 times r1 plus m2 r2 and so forth. Or we could write this as sum over I of mi ri. I use capital letters here. Maybe I used small ones before, so let me change that to a small r. And so that is the center of mass when it is divided by the total mass. And you can see that since this has to be a position, the center of mass, since it's multiplied by mass, I must divide by mass to get rid of those units of kilograms or whatever. Now, we want to be able to talk about things like the velocity of the center of mass. And the velocity of the center of mass is going to be the time derivative, of the position of center of mass. And likewise, we could use the acceleration of the center of mass as the derivative of this. Okay, now how can we relate all of these things together to show that these external forces work properly and so forth? We can take this equation like we did before, dp dt up in this first section, and say, well, P is equal to the sum over m of dr dt1. And here what we're doing is we're not multiplying out the momentum, so I should probably write this out again to make it a little bit more visible to you. We're going to say dp dt. That's the momentum of the whole system and how it changes with time. That's going to be d by dt of, well, what is the whole momentum? It's the sum of mi dri, that's mass times velocity, that's the sum of pi over dt. And I'm going to write that out again so you can see that. This is the sum over I of little pi. And little pi is mi times the velocity. And this then is, as we know, the total external force. But if we look at